In this example, what I want to do is I want to compute an integral. This is going to be an integral, well, let me just say it's the integral from negative infinity to infinity of 1 over x squared plus 1 dx. This is an integral that you do not need complex analysis for, but this integral is nice enough that I want to explain how complex analysis can be used to evaluate this integral anyways. More importantly, there are many, many integrals that you can evaluate using complex analysis than you can using normal Calc 1 and Calc 2 methods. So this is a straightforward integral to evaluate in a Calc 2 course, right? The integrand anti-differentiates to inverse tangent, and then everything's fine. But what I want to do is I want to evaluate this integral using complex methods anyways, and then you can see how this idea will generalize. And this is an idea that we're going to come back to time and time again for the rest of the course. Okay, so we're going to conclude the course with the residue theorem. That'll be one of the last things that we talk about. And this is kind of just a first glimpse into how these integrals can be evaluated using complex methods. So anyway, so let's jump in. So this is going to be this integral of 1 over x squared plus 1 dx from negative infinity to infinity is going to be the limit as r goes to infinity of the integral from negative r to r. And actually, I'm going to change the x's to t's, just because we use t's when we parameterize. And what I want to do is I want you to notice, so this is the quantity that we have to compute now. Okay, so if we can come up with a formula for that, then we're done. We just take the limit and we're done. So this limit right here, if you notice, so I want you to notice that this limit from negative r to r, 1 over t squared plus 1 dt is going to be the integral over the path, which I'm going to call, let's call it gamma naught, of 1 over z squared plus 1 dz, where gamma naught is just the parameterization. So we're just integrating along the line from, say, negative r to r. Okay, so we're just going to go from negative r to r. That path right there is going to be gamma naught of t. So that's just going to be, let's just call it t, where t goes from negative r to r. So we don't need to be any fancier than that. And then what we're going to do to that, and the reason why complex analysis is going to be useful, is that what we're going to do is we're going to make a closed path. So let's look at another curve. Let's say, so that was gamma naught. Let's call this gamma 1. And then gamma will be the union of those two. So gamma 1 is going to be the top half of a circle of radius r, starting at the point r, going to negative r. So gamma 1 of t is going to be r e to the it, where t goes between 0 and pi. And then gamma is going to be the union of those two. Okay, so in other words, take those two curves together, you get a single path. That path, that piecewise smooth path is gamma. Okay, so this is the first point. So notice that the integral that we're trying to evaluate is actually the integral over gamma naught of 1 over z squared plus 1. So it's a path integral. Now, notice also that the integral over gamma naught is going to be, you can think of this. So the integral over gamma naught of 1 over z squared plus 1, you can think of this as the integral over gamma. So the entire curve, 1 over z squared plus 1, minus the integral over gamma 1. Okay, because if you were going to integrate over gamma, what would you do? You'd integrate over gamma naught and then over gamma 1. So here I'm just subtracting. So this integral over gamma naught is the integral over gamma minus the integral over gamma 1. 1 over z squared plus 1 dz. Okay, so now our job is to compute these two integrals and then take a limit and see what happens. Now, this first integral we can evaluate no problem using Cauchy's integral formula. Everything is fine. So for this first integral, this is the easiest one. We're going to have 1 over z squared plus 1 dz. In fact, I think we did something like this. Here we're integrating over gamma. And so we're just going to apply the Cauchy integral formula. This is the integral of 1 over z minus 1, z plus 1 over z minus 1. So we're factoring z squared plus 1 as z plus I times z minus I. Let me write this better. This is the integral of f of z over z minus I, okay, dz, where f of z is 1 over z plus I. Okay, and then we know by Cauchy's integral formula that this is going to be equal to 2 pi I times f of I. And f of I is going to be 1 over 2I, so that's going to be pi. So this integral over gamma evaluated to pi by Cauchy's integral formula. Next, we're going to look at the integral over gamma 1. This one is the one that'll take us a little bit of work here, but the integral over gamma 1, 1 over z squared plus 1, what we're going to do is just apply the parameterization. Okay, so we know that the parameterization over gamma 1 is that this is going to be r e to the it. So this is going to be equal to the integral from 0 to pi, 1 over r squared e to the 2it plus 1 times gamma prime. So that's times ri e to the it dt. Okay, and we're integrating from 0 to pi. And we need to be a little bit careful here. But what we're going to do is we're going to notice that if we take this integral, what I want to do is I want to bound it from above. So let's just see. We're not going to, I don't care if we can evaluate it. I'm not sure if we can evaluate it explicitly or not. I don't care. All we care about, actually, I know that you can evaluate this because we know that 1 over z squared plus 1 has a antiderivative at least over certain regions. But that doesn't matter. So all that I want to do is I want to bound this. And what we're going to do is we're going to apply the m times L theorem. So again, this is going to be less than or equal to the maximum value. So I need to be a little bit careful here. So this is going to be less than or equal to the maximum value over t, as t goes from 0 to pi, times the modulus of ri e to the it over r squared e to the 2it plus 1 times pi. Okay, here I'm actually applying that theorem from Calc 1. We'll just have to edit this. Do, 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 do. Three, 2, 1. Okay, so next what we're going to do is we're going to evaluate the integral over gamma 1 of 1 over z squared plus 1 dz. Now, because this is such a nice integral, it turns out that you can just write out what this integral is, find the antiderivative, everything is fine. You don't have to work too hard. But I want to just show how this works in general, or show a method that we can evaluate in general. So here what we're going to do is we're going to take the modulus of this and apply the modulus times length theorem, or the m times L theorem. This is going to be less than or equal to the largest value that z is going to take, that our integrand 1 over z squared plus 1 is going to take, where z is in gamma 1, times the length of gamma 1. Okay, and so if we remember, gamma 1 was the circle of radius r from 0 to pi. Okay, so that's our gamma 1. And what we can do is a few things. We can apply the reverse triangle inequality. So notice that this is going to be less than or equal to the maximum of z in gamma 1 of a straight line here. Don't need that. So this is the maximum of z in gamma 1 of 1 over the modulus of z squared minus the modulus of 1, which is just 1, times the length of gamma 1. Now gamma 1 is going to have a length pi times r, because it's just halfway. It's half of the circumference of a circle of radius r, so it's 2 pi r over 2. And if z is on the circle of radius r, then the modulus of z is going to be r. So this is going to be equal to pi r over r squared minus 1. Now, importantly, notice that if we take the limit as r goes to infinity of this integral over gamma 1. So remember, gamma 1 is this parameterization that depends on r. So taking the limit of r as r goes to infinity, this quantity makes sense. But this limit is going to be 0. And the reason for that is that the modulus of this is going to be 0 because pi r over r squared minus 1 goes to 0. And therefore, without the modulus, we also get that this limit is 0. And now, finally, we have all the pieces that we need. Okay, so this tells us that the integral, so let's just put all the pieces together. So the integral that we were looking for, so 1 over t squared plus 1 dt, we wrote as the limit as r goes to infinity of the integral from negative r to r of the same quantity, 1 over t squared plus 1 dt. That's just the definition of an improper integral. And we recognize that this is the limit as r goes to infinity of the integral over gamma 2, which of our function, so I might as well write this precisely, which is the limit as r goes to infinity. So the integral over gamma 2 is the integral over gamma minus the integral over gamma 1. And then finally, we just did the hard work of evaluating each of these. The first integral turned out to be pi. The second integral, so this is pi, by the way, for all values r, as long as r is at least 1. So remember that what we used here, and whether I said it explicitly or not, what we used here is that we assumed that I was in this region. Okay, so I is somewhere in here. So that means that r had to be at least 1. But since r is going to infinity, we can just assume that r is big enough and that I is in that region. So this integral turned out to just be pi for all values of r that are at least 1. This integral tends to 0. And so it turns out that this integral altogether is going to turn out to be pi. So the integral of 1 over t squared plus 1, which is a integral of a real function over a real interval. That integral evaluates to a real number pi, but passes through the complex process. So kind of we use the methods of complex analysis to evaluate this real integral. Okay, and so that's a pretty cool thing if you think about it. This is a really nice tool in our tool belt for evaluating these integrals that used to be hard. I mean, this is not a trivial process, but it used to be that some of these integrals are just downright impossible to evaluate. So what I'd like you to try, what I'd like you to do on your own, is try to evaluate the integral from negative infinity to infinity of 1 over x to the 4 plus 1 dx. So this is now officially an integral that the Calc 2 methods are not going to easily evaluate, but I want to evaluate this integral exactly. Okay, so go ahead and try that one.